let's talk about what is complexity. I'll give you a description and some of the attributes. Starting off, misconceptions. Complexity may include, but isn't defined exclusively by these items. One is chaos. That's kind of a technical distinction, and I'll explain that in a second, but a system that's chaotic doesn't mean that it's complex. And I mentioned I raised my hand one time in a conference and said, I asked the question, how are you defining complexity? And the person said chaotic, and I knew right then that they weren't thinking about complexity in the same way that I was. Difficulty in analysis. So you could have a system that's difficult to analyze, doesn't mean that it's complex. For instance, the Tacoma Narrow Bridge can be relatively difficult to analyze depending upon how sophisticated you were. You could imagine something that might require a thermal FEA or some more sophisticated analysis tools. As we'll see, if you can actually simulate it and predict it on a computer, then usually that behavior is not complex. Or complicatedness. So you look at something and it looks complicated and it seems complicated. That doesn't imply complexity either. So what specifically is it? Oh, one other thing. I mentioned the two failures, the Tacoma the Tacoma Narrows Bridge and the global financial crisis. Those were both examples of bad implications of complexity. Turns out that not all effects arising from complexity are bad. Some of them are actually good and should be encouraged, and that's really the science and the field that I think that systems engineers should, that's one reason why systems engineers should study this. We'll talk about that momentarily. Okay, so first of all, system behavior can be defined into 4 different types, and this is according to Stephen Wolfram. He was a mathematician, and he came out with a book called New Science. So he defined system behavior into four classes. The first one is stable systems with single point equilibria. I'll show a graph of what that means here, or a plot of what that means here in a second, but these are relatively simple systems that are resistant to perturbation. So you can think about a ball in the middle of a bowl. So as long as I'm staying within the bowl, it's going to have a single point equilibrium, meaning a single energy point that's stable, and it's going to be relatively resistant to perturbation. Second type are states that are in periodic orbit. So they might look like they're complicated or complex, but maybe you just don't know the sequence. There could be a regular sequence of states. Example would be, they don't really have them as much here in Colorado, but where you are, especially if you're in the South, fireflies. So if you see fireflies at night, you'll see that I think often they will try to synchronize, but they could be in an orbit that's not totally synchronized, but getting to synchronization. Maybe you just don't understand it and it looks random or it looks complex, but it could be, but periodic orbits are one category. And the next higher level up is chaotic systems. Now the distinction between chaotic systems and these other systems are extreme sensitivity to initial conditions. So the classic example that's given is a butterfly in the Amazon flutters its wings and that cascades through a bunch of events and it causes a hurricane somewhere. Maybe not likely, but not totally impossible either. So, and this is, you may have seen this before, but this is called the Lorentz attractor. This is the solution of a certain differential equation. And what happens is that if you change the initial condition, this is a state space diagram. If you change the initial conditions, you'll get a totally different curve. But it winds up giving you, the solutions give you this periodic orbit, which is highly sensitive to what the initial conditions are. As you know, usually if you're solving a typical, say, linear differential equation, I can put in different initial conditions, different initial conditions and wind up, if you think about the ball and the bowl example, I can put myself at different points on the bowl to start out. And as long as it's not too high, I'm gonna still reach the final stable point. This is a little bit different, chaotic systems. And then the fourth level are complex systems. So complex systems have quote unquote regular structure. I'll talk about that in a second. And they have also high information content. The implication to that is going to be trying to predict the outcome, the behavior of complex systems is difficult.